Now let's look at another basic function, 1 over x squared. This is defined, it has a domain. Again, x cannot equal 0, so the domain is negative infinity to 0, union with 0 to infinity. And we can use a table for a graphing calculator again. And we find out that as x is going closer and closer from the negative side, the y values keep getting larger and larger. And as x is going closer and closer to 0 from the positive side, the y values are continuing to get larger. So the y values get larger and larger as x gets closer and closer to 0. And from either side, it's all positive. There is symmetry for the y-axis. So the function goes to infinity as x goes to 0. So the y-axis is a vertical asymptote. Looking at that problem, then the domain is from negative infinity to 0, union with 0 to infinity. The range, looking how this graph, since the rate always came out positive, is from 0 to infinity. It's increasing from negative infinity to 0 and decreasing from 0 to infinity. It's discontinuous, it does not connect. We have a vertical asymptote at x equals 0, the y-axis, and the horizontal asymptote at y equals 0, the x-axis. And let's look at the domain and intercepts here. Well, the domain, if we have 8x cubed minus 2x equal to 0 and solve that, we could factor out a 2x and we'll get 4x squared minus 1 equals 0. So this tells us x equals 0, and 4x squared minus 1 equals 0. We have 4x squared equals 1. X squared is 1/4, so x is plus or minus 1/2. X cannot equal 0, x cannot equal plus or minus 1/2. With those gaps, thinking about putting those in order, I'd have a negative 1/2, I'd have a 0, I'd have a 1/2. So the domain is from negative infinity to negative 1/2, and then we'll have a gap. Then we'll go from negative 1/2 to 0. Then we'll have a gap at 0. Then we'll go from 0 to 1/2, and we'll have a gap at 1/2. We'll union that with 1/2 to infinity. And we can have domains that complicated with rational functions. And then we want the intercepts. So the y-intercept, when x equals 0, I'll fill a 0 in place of the y's. We'll have 1, and then we'll have only zeros on the bottom, so there's none there. And the x-intercepts, where y would be 0, we fill that in. If you have this fraction, 0 equals the fraction, the only way a fraction equals 0 cube is if the numerator equals 0. So this is the only part we have to look at. So we have x squared plus 1 equals 0. X squared equals negative 1, and x would be plus or minus I. That's an imaginary number. So again, there is, for the x-intercept, there is none for this function. Speaking more about asymptotes, if f of x equals p of f divided by q P of x divided by Q of x be a rational function in lowest terms. If the absolute value of the function goes to infinity as x goes to a, then the vertical line x equals a is a vertical asymptote. Notice we have an equation, x equals a number, for the vertical asymptote. Using limit notation, x equals a is a vertical asymptote if the limit as x goes to a, then the function either goes to positive or negative infinity. The line y equals a, again notice it's an equation, is a horizontal asymptote if f of x goes to a as either x goes to positive or negative infinity. Using limit notation, y equals a is a horizontal asymptote if the limit as x goes to infinity of f of x equals a, or the limit as x goes to negative infinity of f of x equals a. Now finding those horizontal asymptotes. Again, we've got f of x equals p of x divided by q of x as a rational function in lowest terms with a degree of q of x is at least 1. So you have to have an x in the denominator. The graph has a vertical asymptote corresponding to each root of q of x equals 0. Now it's each root, so you may have more than one vertical asymptote. If the degree of p of x is less than the degree of q of x, then the x-axis is a horizontal asymptote, and that would be the equation y equals 0. If the degree of p and q equals the degree of q, then the horizontal asymptote is determined by the ratio of the leading coefficients. And if the degree of p of x is greater than the degree of q of x, then we use division to write the function as the quotient plus the remainder over the divisor, and the graph of the equation formed by setting y equal to the quotient is an asymptote. This asymptote is oblique or slant asymptote if the degree of p of x is 1 larger than the degree of q of x, and that's the most we'll use. So, the graph of a rational function may have more than one vertical asymptote, or it may have none at all. The graph cannot intersect any vertical asymptote. There can be at most one other non-vertical asymptote. It could be a horizontal or an oblique, and the graph may intersect that asymptote. Doesn't always, but it could happen.